Now that we know how to create arrays, we need to know how to do math with them. So first things first, two equal matrices, they are defined as equal if they have the same size and the same elements in the same orientation. So for example, over here we have two matrices of the same size, 2 by 2. They have the same elements and the same elements in the same location. So this one is in the same location as this one. However, if we look at these two, they're not the same size, even though they have the same elements. Okay, so these are equal matrices. These are not equal matrices. So on to math. Math in MATLAB is defined in two different ways. First, we have linear algebra operations, and second, we have special MATLAB syntax. These are element by element operations. And these element by element operations are really useful for doing calculations. So like math formulas on numbers in an array. And this is the same calculation on all the numbers. So for example, if I want to do x plus y equals, nope. If I want to do x plus y times, I don't know, z, where x are numbers 1 through 10, y are numbers 10 through 20, and z is numbers 20 through 30. I can do this kind of operation on all of the numbers in my array at one time using element by element operations. So this is my MATLAB syntax for that. Addition and subtraction, those are performed normally. If I want to do multiplication element by element, I have a dot. If I want to do division element by element, I have a dot in front of it. And if I want to do exponentiation element by element, I have a dot. So that's this special dot notation that allows us to do element by element operations on multiplication, division, and exponentiation. So just to clarify, element by element operations look like this. I have two matrices of the same size. My resulting matrix is also going to be of the same size. So a 2 by 3 operated with a 2 by 3 produces a 2 by 3. It's going to take the element in the first location in both of my matrices and do the operation between them. So here represents my operation, and then put the answer right here. So if it was 2 and 3, if it was 2 plus 3, it'd put a 5. If it was 2 divided by 3, it'd put a 2/3. If it was 2 times 3, it'd put a 6. And then it keeps going element by element. So it takes the second element with the second element, does the operation, puts it in the second element. This element does the operation between them, puts it there. And it keeps going through until it has all of the elements operated on each other. That is element by element notation. Really, really useful. But we need to have the dot in front of the multiplication sign, division sign, and exponentiation. Addition and subtraction, totally fine. Okay, so the reason why we need to do that is because matrix operations in MATLAB follow the normal rules of linear algebra, which is not element by element when it comes to multiplication, division, and exponentiation. So we call them matrix operations, and then array operations can be performed element by element. You'll probably hear me interchange the two, but this is what I mean. So let's go ahead and figure out all the linear algebra rules for doing all of these operations. So first things first, addition and subtraction. Addition and subtraction, element by element. It follows your normal intuition, where we're going to take the first element and the first element, add them together, subtract them together to get my resulting answer. If we have scalar addition and scalar subtraction, then it's going to add that scalar to all of the elements in an array. So when a scalar is added to or subtracted from an array, so for example, if I have a1 plus 3, it's going to take that 3 and add it to all the elements. So I would get 5, 1, 6, and 5. If I have two matrices multiplied by each other, it's going to do element by element. So a3 is a1 plus a2. It would take 2 plus 1, negative 2 plus 3, 3 plus negative 3, and 2 plus negative 3 to give me my answer. Same idea if it's subtraction, a1 minus a2, I would do the same thing, except I would subtract the numbers instead of adding them. Matrix multiplication. The default multiplication is matrix multiplication defined by linear algebra. This is different from the element by element. If you want to do element by element, you need the dot. Because matrix multiplication is a bit confusing usually the first time for students. If I want to multiply a scalar times a matrix, that's totally normal. So if I have K1 times A1, it would just take the 2 and multiply it by all the numbers. So I get -8, 8, -6, -6. Same thing if it's a fraction. If I have K2 times A1, that would be normal. Take this scalar times all the values. So 2, -2, 2/3, or 3/2. And 3/2. That one's not confusing, but the matrix multiplication tends to be a little bit more confusing for students the first time you go through it. So if we have just the asterisk, it's going to do this. It's going to do the dot product between all of the rows in A and all of the columns in B. So matrix multiplication is just a dot product over and over and over and over and over again. If you don't remember how to do the dot product, the dot product of two vectors, so the dot product is performed between vectors, and the result is going to be a scalar. So one caveat, the dot product can only be performed between two vectors of the same length. So for example, if I have v1 times v2, here or there, both have the same length, they both have 3 elements. It doesn't matter if they're rows or columns. And my dot product equation looks like this, where this sigma here, this indicates summation. So I'm adding up a bunch of numbers. I'm calculating the sum between a bunch of numbers. This is the element by element multiplication between the two vectors. So for example, I'm going to do element by element multiplication with these two. So I take 3 times -3, 5 times -2, -3 times -3, and sum them all together, add it all together. So my dot product between v1 dot v2 is going to be -10. Note, my answer here is a scalar. The dot product between two vectors is a scalar. These vectors need to have elements of the same size, or the same number of elements. So, matrix multiplication, it's just the dot product between the rows in the first matrix and the columns in the second matrix, and we repeat over and over and over and over and over again. So formally, if we were to define it, this is what all of this describes. So first things first, if A and B are two matrices, the operation A times B can be carried out if and only if the number of columns in matrix A is equal to the number of rows in matrix B. So we call that the inner dimensions, and we can write it out like this. If A is an m by n and B is an n by p, if these two numbers on the inside match, then we are good to go. We can perform matrix multiplication. Otherwise, we can't. So matrix multiplication can only be performed on some matrices. Also, the order matters. This needs to match with this. My resulting matrix is going to have the same number of rows as A and the same number of columns as B. So that means my resulting matrix is going to have m rows and p columns. So if I have these two matrices over here, A1 and A2, A1 is a 2 by 2. If I multiply that with A2, which is a 2 by 3, I have to check to see that the number of columns in A1 matches the number of rows in A2. These match, I'm good. My resulting answer matrix is going to be a 2 by 3. So my result is a 2 by 3. So that means if my answer is a 2 by 3, I have 6 dot products in order to find the answers in this matrix. So element I, j in the product matrix, in order to find each of these values, I need to do the dot product between the rows in matrix A and the columns in matrix B. And this is what this formally looks like. This is what this matrix formally looks like. There's a way to remember it. So if I want to find row 1, column 1 in my answer, I'm going to grab row 1 in A, column 1 in B, and perform the dot product between them. If I want to find row 1, column 2 in my matrix, in my answer matrix, I grab row 1 in A, column 2 in B, do the dot product between them, and continue. If I want to find row 1, column 3, I would go ahead and grab row 1 from A and column 3 from B, etc. So if we see this play out in our answer over here in our matrix, so here, let me make this bigger, write it bigger. So if I want to demonstrate in this matrices over here, I'm going to start with row 1, column 1. So I'm going to grab row 1, column 1. So that the dot product between those two, 2, -1, dot with -3, 5, produces 2 times -3, these numbers, plus these numbers, -1 times 5, or -11. Gives me a -11. If I want to find my next number, here I have row 1, column 2. So I'm going to grab row 1, now column 2. Do the dot product. So 2 times -4 plus -1 times 4. Or -8 minus 4, -12. Keep moving over. If I want to find row 1, column 3, I take row 1, column 3. Do the dot product. 2 times 0 plus -1 times -2, or 0 plus 2, which gives me 2. And then I keep going. Down here, now it's row 2, column 1. So I'm going to grab row 2, column 1. Dot product. 3 times -3 plus -5 times 5, or -9 minus 25, which is -34. 2, column 2, so I'm in row 2, column 2, so I grab row 2, column 2, dot product. Three times -4, -12 plus -20, which is -32. And my last one, I'm in row 2, column 3, so I want to grab row 2, column 3, dot product. Which is 10. And there we go. I have done 6 dot products in order to find the 6 elements in my resulting matrix. So before we do matrix multiplication, we first check to see if we can. And then we fill in our resulting matrix, which has the same number of rows as A and columns as B, and do all of our dot products. Keep in mind, our order matters. A1 times A2 is possible, but A2 times A1 is not possible. Cannot do this because A2 is a 2 by 3, A1 is a 2 by 2. This does not match this, so therefore I cannot do my matrix multiplication between A2 times A1. So order matters when it comes to matrix multiplication. Order matters. Okay, last one to go over is matrix division, which, as it turns out, matrix division is not defined. It's not defined. We cannot do matrix division. But we still have matrix operations that MATLAB does. So we can do A divided by B, and we can also do A left divide B. Both of these exist in MATLAB. What it's doing when we type that is not dividing the two matrices. It's multiplying by the inverse. So if we take a scalar, 5, and I multiply it by its inverse, I get 1. This is my inverse of a scalar. We have an analogous, we have the same analogy, we have something similar in matrices, where if I take A times A inverse, I get what's called identity. We don't write it as 1 over A because it's not what it is, so we write it as the inverse. And same thing, A inverse times A also equals identity. So that's what these division signs are doing in MATLAB. If I do normal right division, it's A times the inverse of a matrix. If I do A left divide B, it's the inverse of A times B. Okay, so what in the world do all these things mean? Here, this is identity. Identity matrix is analogous to the 1 as a scalar. It's a square matrix full of zeros with 1s on the diagonal. It's the one we create with the I function. Here you can see the identity matrix for a 2x2, a 3x3, and a 4x4 that I already have written down. And it turns out if we do A times its inverse, we get identity. And here the order doesn't matter. Same thing, if we do A inverse times A, we also get identity. Kind of like if we do 5 times 1/5, it equals 1, or 1/5 times 5 also equals 1. Only square matrices can have the inverse, and not every square matrix has an inverse. So here we have the equation in order to find the inverse of a matrix. A inverse equals 1 over what's called the determinant. So this is the determinant of a matrix. It's not the absolute value. It is determinant of a matrix. So 1 over the determinant of a matrix times A adjoint. And we can see that if we have 1 over the determinant, that means if our determinant equals 0, then math blows up. We cannot have that situation. So if a determinant is equal to 0, then our matrix is considered singular. So you'll see this word in MATLAB errors. It's singular, which means its determinant is equal to 0, and then the inverse does not exist. So if our determinant is not equal to 0, then we are good, we are fine, we are happy. Our matrix is non-singular, and it's invertible. So that's why some matrices, some square matrices, have inverses and some do not. But we can only check for a square matrix. If we want to calculate the inverse, we can follow these steps. First, calculate the determinant. Determine if the matrix is invertible or non-singular. For MATLAB, we can use the determinant function. And that's pretty much what we're going to go with for now until we get to linear algebra later on after spring break. So we can find the determinant. If it's equal to 0, stop. If it's not equal to 0, then we're good. Keep going. Once we go ahead and determine whether or not the determinant is equal to 0, then we can go ahead and to find the adjoint matrix. A adjoint. There's our symbol. We don't have a function in MATLAB in order to calculate the adjoint matrix, but we do have the inverse function in MATLAB, which can be used to find the inverse directly. Once we have the determinant, once we have the adjoint, we can go ahead and plug it into the formula. So for a 2x2 matrix, we will focus on 2x2s. We will get to bigger matrices later on. But for a 2x2, here are our steps. To find the determinant of a 2x2, we take A times D minus B times C, where A, D are the elements along the main diagonal here, and B and C are the elements on my other diagonal. So I like to draw a little fish here to demonstrate what we're doing. 4 times 3, A times D, minus -1 times 2. These elements minus these elements. So that means my determinant here is 12 minus -2, 14. My determinant of A is equal to 14. That's not equal to 0, so we're good. We're happy. We can go ahead and move on. To find the adjoint matrix, it looks like this. A and D switch places. B and C go ahead and change their sign. So A adjoint. A and D switch places. So 3 and 4 switch places. The -1 and the 2 change their sign. So -1 becomes 1, 2 becomes -2. And then I have all my pieces. So the A inverse equals 1 over the determinant times A adjoint. I can write this multiplying that scalar multiplication. So 3 over 14, negative 1/7, 1 over 14, and 2/7. And there's my answer. There's A inverse. So I can do it for 2x2s because it's relatively easy, straightforward. For 3x3s and bigger, we're going to have to wait until later on in the semester. The reason why we even care about doing all this is because our main application in this class is solving systems of linear equations. And it turns out linear algebra rules provide a really convenient way of writing and solving systems of linear equations. We've seen systems of linear equations for quite a while now in math. They look like this over here, where all of our unknowns are raised to a power of 1, and we have more than one unknown. So there's no polynomials. It's not one variable, one equation. We have multiple unknowns here. We have x and y, multiple equations. X and y are both raised to a power of 1. We cannot get any higher. They are linear equations. And here you can see a generic form of a linear equation. Same thing here. Same system of equations. But we can see our unknowns. Oops. Our unknowns. Here they're y's. It doesn't matter the letters. But all of our unknowns have coefficients in front of them, and then we have constants on our right-hand side. If we have this scenario, we can go ahead and write our system of equations in matrix format, where we have ax equals b or yc equals d. These are the same things, they're just transposes of each other. I'm going to focus on ax equals b, where A is our matrix of coefficients. X is our matrix of unknowns. These are our letters in our system. X, Y, X1, X2, X3, etc. And then we have a vector B. B is our vector of constants from our right-hand side. And what we do is we take our system of equations and we go ahead and place all these numbers and letters into each matrix. For the X matrix, we'll start there. For the X matrix, we just fill it with our unknowns. I have an unknown, whoops. I have unknown X, unknown Y. So X, Y. Fill it with my unknowns. For my B vector, I have my constants. Put the constant from equation 1 in the first one, from equation 2 in the second one. So that one's a 10, this one's a 16. And then if I had 3 equations, I would have another one, 4 equations, etc. It would just keep going down. To fill my A matrix, for my first row, I'm going to take my coefficients from equation 1, from second row, coefficients from equation 2. In each column, I have my unknowns, so X, Y. So for A, for equation 1, the number in front of X here is a 3. The number in front of Y is a negative 2. The number in front of the X in equation 2 is negative 1. And the number in front of Y for equation 2 is a 4. And there we go. I have filled my A matrix with my coefficients from my system. Notice X, Y matches this. They need to be in the same order. And there we go. I have written my equation, my system of equations here, in matrix format, AX equals B. If we do that, then my solution, you can see the math here, my solution ends up being X equals A inverse times B, or in MATLAB notation, X equals A left divide B. Similarly, if I have YC equals D, it's the same thing. Y is the transpose of X, C is the transpose of A, and D is the transpose of B. So we will focus on AX equals B, and if you want to do YC equals D, that's totally fine. The solution here is D times C inverse, or D right divide C. So that's going to be our main application, and we'll do a couple 2x2 systems in order to go through this process. But really, we want to focus on being able to write our systems of equations in linear format, because then if we know that, we can solve any system by using this one single line.